In Chapter 2.1, we're going to look at quadratic functions, their graphs, and their various forms. We'll start off with what tends to be what we would call the standard form of a quadratic equation or a quadratic function. That's in standard form basically has them all multiplied out and will take on a look like f of x equals ax squared plus bx plus c. Kind of that normal type of looking quadratic function that we would be presented with if you're looking to factor and do things with. So we established that a, b, and c are real numbers, and which means they can be zero, except a cannot be zero, because if a was zero, that would eliminate the term that actually makes it quadratic, and you'd be left with bx plus c, which is a linear function. So the only stipulation is a can't be zero. So it's possible for us not to have a bx term. B could be zero, or you could not have the plus c part, but you've got to have the x squared part. That's literally what makes it a quadratic function. Now, we always talk about h and k as being the place of the vertex. That's especially when it's in vertex form. But if it's in this form, we don't have an h or a k, but we can locate h. If we take the opposite of b and divide that by 2a, that'll give us the x value where the vertex is located. And then once we have the x value, we can plug that into the function. So find the f of negative b over 2a. That gives me the y value, which is the k. And so the vertex will be located at the opposite of b. Whenever we see a negative in front of a variable, it's helpful for us to think of it as meaning the opposite sign of. So if this is a subtraction of b, then we would take the positive. If this is a plus b, we would take the negative of b and divide that by 2a. And then finding the f of the opposite of negative b over 2a. All right, and just like we've seen with the vertex form, which we'll look at before, the a value, which is the value in front of x squared, gives us a lot of clues actually as to how the quadratic function looks. If a is greater than 0, meaning it's positive, then we have an upward facing parabola. If a is less than 0, so it's negative, then we have a downward facing parabola. So a functions the same way as it does in the other form, which we'll be reminded of here in a little bit. Also, if a is a value greater than 1, and I take the absolute value of a because whether a is positive or negative, that's really what determines if it's upward or downward facing. But looking up the absolute value of it, if it's a value that's more than 1, then it's stretched vertically. And it can be stretched vertically going up or stretched vertically going down. But if the absolute value of a is a fractional value, like a half or a third, then we are going to see it visualized as a compressed parabola. Also, every parabola has what we call a axis of symmetry, which is a vertical line basically that goes through the h value of the vertex. So it's at x equal to negative b over 2a. X equal to any constant, any number, is always a vertical line. But this is a vertical line that we specifically call the axis of symmetry. And then lastly, just like with all other graphs, if we want to find the y-intercept, we find the f of 0. That'll tell me where, since that means we're plugging in 0 for x, that always gives us the y-intercept. And if I plug in 0 for x, well, 0b, right? So 0 for x, and then b is the y-intercept. If we want to find the x-intercepts, we find the f of x equal to 0, and we solve for x. So we find out where x is when y is equal to 0. So if we're given an equation in standard form that we know is a quadratic, let's look at finding the vertex, the axis of symmetry, and describe the value of a on the graph. And so looking at what we have here, we know that let me put this in a different color here, but the vertex is going to be at the opposite of b over 2 times a. And then once we have that value, we're going to substitute it in to the function f for x, and then come up with the y value at that x value, h. So, well, let's just start. We have our a, b, and c. A is 2, b is 8, and c is 10. We don't really need c in this case, but the opposite of b would be negative 8 over 2 times a, which is 2. And so that gives me negative 8 over 4, which is negative 2. So for the vertex, which I'm looking to find here, we know that negative 2 is the x value, h, and now we need to find its corresponding k. So we find the f of negative 2. So 2 times negative 2 squared plus 8 times negative 2, and then plus 10. So negative 2 squared is 4. So 4 times 2, this is negative 16, plus 10, so that's 8, plus negative 16, plus 10. Well, 8 plus negative 16 is negative 8, and negative 8 plus 10 is 2. So 2, 2 is the vertex for this particular function. So negative 2, 2 is going to be right there. Given the axis of symmetry, we know is at x equal to h, so we know the axis of symmetry, which isn't really part of the graph. It's more or less the line about which my parabola is symmetric. So I'm going to draw it as going upward there. I'm just going to draw it in there, kind of a dotted light line. And if we want to graph the parabola, I'm simply going to plug in points that are on either side of the vertex. So looking at my x values, we're at negative 2. I'm going to plug in negative 1 and 0, and then to the left of 2, we'll go negative 3, negative 4. All right, so a couple to the right, a couple to the left. I don't want to get too far, especially since I know it's being stretched. I might quickly run out of space. But negative 2, 2, we know is one of my points. We also know it's going to point upward because a is equal to a positive 2, so that tells me that. All right, plugging in negative 1, if we find the f of negative 1, f of negative 1 is 2 times negative 1 squared plus 8 times negative 1 plus 10. So that's 2. Negative 1 squared is 1, so 2 times 1 is 1, plus negative 8, plus 10. So that's 2 plus negative 8 is negative 6, and negative 6 plus 10 is 4. So negative 1 will be 4, and I'm assuming negative 3 will be 4, but I'm going to double check just to make sure I have the right. If I get that pattern, that gives me confidence that I'm in the right spot here. So negative 3 squared plus 8 times negative 3 plus 10. All right, so negative 3 squared is 9. 2 times 9 is 18. And then 8 times negative 3 is negative 24. 18 plus negative 24 is negative 6, and negative 6 plus 10 is positive 4. So we see it. We've got that symmetry here. Negative 1, 4, we've got a point. Negative 3, 4, we have a point. Now let's go to 0. 0, if I ever have an option to plug in 0, I'm definitely going to take it, because 0 is an easy number to plug into by function, as we'll see really quickly. Now, since we've established symmetry, once I have this, I can know what the f of negative 4 will be. So 2 times 0 squared plus 8 times 0 plus 10, well, anything you multiply by 0 becomes 0, so we get 10. That tells me negative 4 also has to be 10. That's way up here, and then 0 and 10. There's enough points here for me to do my graph. And there we have it. We graphed it while it's in standard form. The other form of a quadratic function that you guys have been exposed to, at least so far in our class together, is the vertex form of the quadratic function, where we have this part here that involves the square. We have it done such that we can see what the h and the k are. So in this particular form, we don't have to find the opposite of b over 2a and all that. We can simply look at this form and immediately see and find the vertex. The vertex is at hk, so that's why this a lot of times is referred to as the vertex form of the quadratic function, because it automatically reveals the vertex. In a same way, the value of h, which is the value of x, the x value of my vertex, is the axis of symmetry. It is the vertical line that the parabola is symmetric around. And if a is greater than 0, it opens up. If a is negative, the parabola is going down, so the value a is out here. Absolute value, if it's greater than 1, so that stretches it vertically. We're multiplying it something that makes it exponentially larger, makes the y larger. I might have said larger, but I meant to say larger. And the absolute value of a is a fraction, basically. So between 0 and 1, we say it's compressed vertically. F of 0 will yield the y-intercept, 0b, and the x-intercepts can be found when we substitute 0 in for f of x. Of course, when you do that, you've got to usually factor or find other ways to find the solutions of the quadratic function. Let's see, like with lines, equations of lines, can we find the equation of the quadratic function if we're given some clues as to its location? One of the big clues we can be given is the vertex. In fact, if we know the vertex, all we need is one other point to find the equation of that function in vertex form, or standard form if you want to eventually put it into that. But the vertex reveals two very important parts of the function. If we look at the vertex form of the quadratic function, f of x equals a times x, the variable spot, minus h, just put an h there, plus k. Actually, if I'm going to not put that there, I'm going to put this in here, blank spot. This is where the k will go. So take note that it's always h is a subtraction in front of it. K has a plus in front of it. And so when I substitute these values, negative 3 for x and 4 for k, you'll notice over here with that h, this is a subtraction, so we want to make it plus positive 3. Okay, we always want to clarify that, if not just for ourselves, for anybody who's examining. So this is what we have so far. We have our f of x over here, which is basically our y, right? We have the a value that we're not sure about yet, and we substituted our h's and k's. Now, the other clue that we're given is a point it passes through. This is like one particular pair, negative 4, 7, that we know the graph will cross. That's an x and a y. And so the one thing I really need to find here, because x and y are going to be a part of the overall function, is I don't know what a is. And so I'm going to use negative 4, 7, the other point it passes through, as a way for us to get to a. So temporarily, I'm going to put in 7 and negative 4. Why? Because this eliminates the variables, at least temporarily, so I can only have one value left, one variable left that I can solve for. I already put in the h's and k's, and now I know this is another truth part, that negative 4, 7 is a point that's on my line, and so we can temporarily use it, so to say. So let's simplify. So negative 4 plus 3 is negative 1. Still have my a there. Plus 4, 7. Well, negative 1 squared is just 1, so that just leaves me with a plus 4 equaling 7. So if I want to solve for a, I just want to subtract 4. I see that a is equal to, that's a subtraction of 4, a is equal to 3. And so that gives me the full-on rest of my equation, which really was just lacking the a. So we have 3 parentheses x plus 3 squared plus 4. There's the equation on my line where I know that the vertex is at negative 3, 4. Oops, negative 3, 4 would be right here. And so we want to get a couple more points there. So we'll put in x, and let's see, negative 3, 4. So let's plot a couple points on either side. Negative 2, we'll find that, and then negative 4. Plugging in negative 2, negative 2 plus 3 is 1. So that gives me 3 times 1 squared plus 4. That gives me 3 plus 4, which is 7. So negative 2 gave me 7. Would negative 4 give me the same thing? Well, negative 4 here plus 3 is negative 1 squared, which becomes positive 1, and we end up with the same outcome. So we know we have that symmetry on either side of the parabola. So 2, 7, negative 4, 7. That's as far as I'm going to plot, because every other point is going to be way off the mark there. For example, 2 squared, or if I plug in negative 1, that gives me negative 1 plus 3, so 2. 2 squared is 4. 4 times 3 is 12, and 12 plus 4 is 16. So that puts me way off the mark. But as long as I know the parabola and what it tends to look like, I'm good. I just need a couple of solid points on either side. And if I can't graph anymore, then we'll just leave it at that. Okay, so if we are given a equation that's in standard form, how can we actually just get it into vertex form? One of the ways that we can do that, because vertex form does tell us a little bit more about my function, is this process called completing the square, which you may have used when you were solving quadratic equations that were set to 0. It's one of the ways that we actually come up with the quadratic formula. But we can also use this process to change an equation from standard form to vertex form. To go from vertex to standard, all I need to do is to carry out the multiplications. For example, let me just take this function here. We have f of x equal to 3 times x plus 3 squared plus 4. If I actually carry out the multiplications here, so for example, take x plus 3 and square it, that's x plus 3 times x plus 3, so that gives us x squared plus 6x plus 9. And then distribute the 3 here. That gives me 3x squared plus 18x plus 27. We had plus 4. And then, combine like terms, I see that 3x squared plus 18x plus 27 plus 4 is 31, so plus 31. This would be the equation in standard form. So we just carry out the multiplication. But how do we go the other way? And we're going to do that through a 2 or 3 step process. Some are a little bit easier than others, but here's our directions. We want to convert this function to vertex form. All right, so first step is to identify a, b, and c. In this case, a, there's nothing, a would be the value in front of x squared there. A is just a 1. B, the value in front of the x term, is negative 2. We want to always pay attention to the sign there. And then c is 2. All right, so we identified that. if a is equal to 1, we would go straight to step 2. But if a is not 1, we're going to factor it out. And I'll show you what we mean by that on another example here. But the main thing we have here is we want to rewrite this. And I'm just going to go ahead and start this process over here. I want to put parentheses around the first two terms. So x squared minus 2x, and then I'm going to leave a space here, plus blank square, or nope, not squared yet. Can't do that. All we did was put parentheses there. So I put parentheses, I left a blank spot. The plus 2 part of it, I'm just going to leave outside of the parentheses. So all I did was rewrite this so that the parentheses are including the first two terms, the x squared, the minus 2x. I left this part out, and I left some blank spots. So I basically did this, but then I rewrote it with some blank spots there because we're going to add something. What we're going to add is going to make this, the part that's in the parentheses at least, a perfect square trinomial that we can factor down. We take half of b and we square it. Well, b is negative 2. So if I take 1/2 times negative 2, and then we square that result. So let's make sure I do that. We're squaring not just the negative 2, but the product of negative 2 and 1/2. So that gives me negative 1, which squared is positive 1 in this case. So I'm going to add that here in the parenthesis. So I added 1. And to keep this equation in balance, I need to do something out here to keep it in balance. Notice that the equal sign is way over here. Normally when we add things to functions, we add it on one side and then we add it on the other side to keep it in balance. But here I'm actually adding something and then wanting to balance it out over here. So rather than adding 1 to the y and then having to move the 1 to the other side, so I want to keep it solved for y, if I add 1, I'm going to add negative 1 over here. And that way I really haven't added anything to the right-hand side. I added 1, but then I'm counterbalancing it over here by subtracting it. So I've still kept my equation in balance. And now this part is a perfect square trinomial, where we can write x plus, and then whatever 1/2 of b was before we squared it. And before we squared it, half of b was negative 1. That ends up being what goes in here, negative 1. So in other words, let's simplify this down. Instead of having x plus negative 1, I'm just going to put x minus 1. And then we simplify this. This is plus 1. And this is my function in vertex form, x minus 1 squared plus 1. So my vertex is at 1, 1. Actually, remember we take the opposite of h. So we're at 1, 1 as my vertex. So that was my step 3 here. Once I added half of b squared to each side, add it to one side, but then subtract it outside the parentheses, this factors down. X minus 1 squared is x minus 1 times itself. So that's x squared minus inners and outers minus 2x plus 1. You can see all I did was factor it. And one of the key things once you factor it is if you have the perfect square trinomial, what will always go there is whatever 1/2 of b was before you squared it. So now, of course, graphing the function f of x equal to x minus 1 squared plus 1, the vertex is at hk, which is 1, 1. Remember the general form, I'm going to rewrite it here, a times x minus h squared plus k, that we always do the opposite when it's in front of the h, right? So if I'm looking at x minus 1, which is what I have here, h would have to be 1. If h has a value 1, x minus 1 is what I see. If x was -1, we would actually end up with x plus +1, right? But that's not what we have. We have x -1, and so h is actually 1, not -1. And then the k is whatever we have out there. It's kind of like when we were talking about the horizontal shifts and all that. We always did the opposite of what we saw. That was the value of h. So we know we're at 1, 1 for our vertex. And the a value out here is basically a 1. So that tells me there's no compression, no stretching, and it's facing upward. And we use our knowledge of the vertex at 1, 1. I'm going to plot from 1, 0, and -1. So a couple to the left, 2 and 3, a couple to the right. And hopefully, especially when I plug in 0, I find the f of 0 here. We see 0 minus 1 squared plus 1. Well, -1 squared is 1, and 1 plus 1 is 2. So 0 gives me 2. I can assume 2 would do the same thing. If I plug 2 in there, 2 minus 1 is 1, and 1 squared is 1, plus 1 is 2. So these both give me 2. So if we find f of 3 now, that's 3 minus 1 squared plus 1. 3 minus 1 is 2. 2 squared is 4. 4 plus 1 is 5. So 3 gave me 5. -1 I can assume is going to give me 5 too, because I've already established the symmetry, and both 3 and -1 are the same distance from that h value on the vertex. Let's plot these out. Let's see. 2, 2 is a point, 0, 2. Then -1, 5. And 3, 5. And here's my parabola. Remember, it's not a V here at the bottom. It's very much a U-shaped curve. So make sure you've got that. And these are continuing to get steeper and steeper as they go, but they never get vertical. So we just kind of try to show that, and we draw arrows on the ends of our curve. Let's try something a little more difficult and see how far we can get. Now, one of the tricky parts we talked about here was, excuse me, step number 1. Well, first, identify what A, B, and C are. Here we have A is a 3, B is -12, and C is -7. And I put parentheses around that first, but I'm going to rewrite this, and I'm going to leave more space there. So 3x squared minus 12x space there, and then -7. Now, the first thing it talks about is factoring out a. If a is not equal to 1, we have to factor it out. So actually, I'm going to rewrite this one more time, factoring out the 3. 3 and 12 go into each other, but regardless, doesn't matter. We have to get a 1 here in front of the x squared inside the parenthesis. So if a is something other than 1, we have to divide it out. And so that's going to give me -4x. And then, of course, we're going to add our blank spots here. Great. So I'm set now. I've got inside the parentheses, I factored out the a. And this gives me a -1 in here. I'm sorry, a +1 in here, which is what I needed. Now what I'm going to do is I'm going to look at b. And b is actually different now that I factored out. It's a -4. So as I look at what I'm going to add to both sides, I'm going to take the opposite of b, the negative. I don't know. I'm thinking of a different formula. We're going to take 1/2 of the b value, which is -4. And we're going to take that and square it. So 1/2 of -4 is -2, and -2 squared is +4. So 4 is what I'm going to add inside my parentheses. Now remember, we want to do the opposite here. So because I added 4, I want to balance out the equation. But I actually did not add 4. That's what we see inside the parenthesis. But remember this 3 out here. This 3 is, the 3 is tagged to every term. So by adding 4 in this spot, I've actually added 4 times 3 to my equation, right? By putting it in there, this 4 is going to get multiplied by the 3. And so in reality, what I've added is 12, which is what I need to balance out here. So I add negative 12. This is negative, that's positive 4, this is positive 3. So I added 12, I want to subtract that out there. So let's rewrite what I have so far then. We have f of x equals 3 times x minus 4x plus 4, and then minus, it looks like 19, negative 7 plus negative 12. What I have in here, once I've added that, is a perfect square trinomial. And so I'm going to factor that. And whatever's going to go in here is whatever half of b was before I squared it, which half of b was negative 2. So this is x minus 2 quantity squared. This tells me a few things about my function. Number one, it is it's in vertex form, and its vertex is at 2, negative 19. It's upward facing, and it's been stretched because it's being multiplied by a factor of 3. There is another way that we can convert this function to vertex form. Writing out vertex form, of course, we can, it would look like this. And in fact, starting out, we already know what the a is in this case. The a is 3. When it's in standard form, which is what most books call this form, ax squared plus bx plus c, I already know what a is. This is ax and this is an a here. We keep those variables the same in the general form for a very specific purpose, because they will be the same once we convert it. Squared plus bx plus c. So, c, not 7. So we see c is negative 7, b is negative 12, and a in this case is 3. So I've already got one of the points here that I need to find, right? So actually, let me go ahead and just rewrite this. I've got 3 here, or a, sorry. And so I'm kind of trying to fill in the blanks, right? The only thing I have left now, once I've figured out a, is the h and the k, right? So another way for us to find this is simply to convert it, is to find the vertex, the h and the k, because in vertex form, h, k are my vertices, well, the vertex of the parabola. So remembering when it's in standard form that negative b over 2a will be the h value, or the x value of my vertex, and the f of negative b over 2a represents plugging that into the function and then finding the solution. So in this case, b is negative 12, so the opposite of 12 is positive 12. Remember, we think of the negative in front of a variable as meaning opposite sign. And then we have 2 times a, which is 3. So this is 12 over 6, which is 2. So I see for my vertex, h has a value of 2. And then to find the y part, we need to find the f of 2. So we're going to plug this actually into the function and go ahead and solve this. So we write out 2 wherever we see it. And then we simplify all this. 2 squared is 4, so that's 3 times 4 minus 12 times 2 is 24. Minus 7, so that's 12. Minus 24 minus 7. That's negative 12 minus 7. 12 minus 24, and that's negative 19. So we see 2, negative 19 is where my vertex is. And so we can plug that directly into the function here, 2 and negative 19. Notice that when I plugged it in, what I see here is minus 2, because in the formula we have this subtraction. And so plugging in positive 2 keeps that as a subtraction, but what we see is negative 2. Right? That's why the h is always the opposite sign. The actual value of h is the opposite sign of what we're seeing. But the value of k is what we see. You could write it as plus negative 19, or just minus 19 instead of plus negative. Either way, this is an alternative way and a much simpler way, really, of finding or converting from standard form to vertex form. I'd also like to work through a problem where we're going to try to find the actual quadratic function given some information, namely given its vertex and given a point that it passes through. So the general form of my quadratic function, actually this would be the vertex form, excuse me. If I know the vertex, I already have half of what I need. I have the 10 and the 2 here as my vertex. That means that's my h and k. So right away, I can fill in part of the unknowns, which here the unknowns represent h, k, and a. I'm given h and k when I'm given the vertex. So now I only have one more goal to achieve. So I did want to point out I forgot to put this there at first. X minus 10 squared then plus 2, filling in my h and k. Notice that the h looks like the opposite sign now, minus 10, but that's h has a value positive 10. But then the k is, and that goes back to the signs we see in front of those variables. It's a plus k and a minus h, so h will always look the opposite of its actual value. Once it's in that function, of course. Now all I have to find is a, and when I'm given a point that it passes through, I'm given a x and y that we know are a solution to this function, right? So this would be my input, this would be my f of x, my y output, and so if I substitute these in temporarily, leaving a there, I have a relationship that I know exists, that when the input of negative 6 is, input into my function, the result is 0. And those, we could be given any numbers. We're lucky in this case to be given a 0 because they just always happen to work out nicely. But now there's only one variable, a, that I need to solve for here, and we can do that. So a, this becomes negative 16, which we're squaring plus 2. And so we want to start simplifying this out. So I'm going to subtract 2 on both sides. That gives me negative 2 equals a times negative 16 squared. Well, 16 squared is kind of a large number, but it is 256. And so then if I solve this for a, we'll divide both sides by 256. And we have a has a value of negative 2 over 256. That's the remaining value I needed here to write out this function. And we're just going to substitute that in there. And we have found our function. We kind of knew it was going to point downward because this was my vertex 10, 2, which is way up in the first quadrant. And yet it does pass through negative 6, 0. So it's going to pass through a point that's below it. That tells me it's going to be upside down, and hence the negative there for my function. I want to look at doing some functional kind of analysis with our graph here. Let's say we're given in a graph, which we have here. We've been given the equation for the graph, but then we've also been given a graph of the graph. And we're asked to find the domain in the range of f. Now, when we talk about the domain, domain is what we're allowed to plug into our function. And looking at our function, we have to ask ourselves, is there anything we are not allowed to plug in here? And because there's no way for me to get 0 in a fraction or negative under a square root, I know the domain of this function is negative infinity to positive infinity. I can also look at my graph here and see kind of what's going to be happening with the x, right? This graph continues to go down and out for the rest of infinity and beyond, and we can see that every x value will eventually go to some y value. It's just going to get really negative really fast. But looking at the x-axis, we see that there's really no place where we never start. We're not allowed to put any more negative numbers in. It's just going to continue to get lower and lower and lower. And so negative infinity to positive infinity. In fact, every parabola, unless there's something off about it, something unique or weird about it, has the domain of all real numbers. Okay, I'm going to go ahead and erase this. Let's talk about the range. We talk about the range. The range is the what's a little harder with just for us to determine just with our function, unless we know where the vertex is and we know that it's an up or down facing parabola. But the range has to do with the y values. So as I'm looking here, I'm looking at what type of y values am I getting? And we're getting all kinds of y values, seemingly infinite ones, right? It's going to keep going down and down and down. So all the y values that we get seem to be somewhat infinite, except we have one limitation, and that's up here. It actually is never going to go higher than this y value here, which is 3. So my range goes from low to high, because when we do interval notation, we're always going lower boundary, upper boundary. In terms of y values, that would be the lowest to the highest value, lower boundary, upper boundary. There is no lower boundary, so we have negative infinity there. And then our upper boundary never gets any higher than 3, and it's actually the vertex, so it's included as a number in my range. So negative infinity up to 3. Now, B part of this asks us about, gives us a question about the inequality. This is the function we have. This was f of x, right? Our f of x was equal to this. In other words, our y's, right? So we plugged in values for x. We simplified all this down, and the result was always the corresponding y value, right? So when I put in 2, for example, 2 squared is 4. 4 times negative 2 is negative 8. Negative 8 plus 8 times negative 2 is negative 16. So we have, and I think I made a mistake here. This wasn't negative 2 we substituted. It was positive 2. I was looking at the negative 2 there for A. So this is actually plus 16. So I have negative 8 plus 16, which is 8, and then 8 minus 5 gave me that 3. So 2, 3, right? So that gave me the y value. This expression represents all the y's. And so when we have the expression f of x basically greater than 0, we're talking about the values where the y is positive. So looking at my graph, can I tell where the positive y's are? And in this particular case, we can. We can tell where the y outcomes that are positive are. They're all the values above 0, going up to 3. So what are the x values that give us those y values? So the part of the function, the x values that correspond to y outputs, go from where I'm intersecting here. And The values where they're intersecting are the x values here, which they gave to us. It's kind of, they gave it to us in an awkward way, but they gave them to us. So when we say solve the inequality, we're trying to find the x values that result in values greater than 0 for that expression. So the x values from lower to upper are going from 2 minus square root of 3 halves all the way to 2 plus 3 square root of 3 halves. We are touching this. Well, no, we won't touch it. It'll be a parenthesis because it's just greater than, it's not equal to, and we'd have a parenthesis on both sides. This is the area from here to here for x that results in y's that are greater than 0. And if we were talking about the y's that are less than 0, it would be all of these values in my two legs here. So we'd have to go from negative infinity up to this point, and from this point to positive infinity for x. That results in negative values. A little bit harder to see, but again, this is not an ordered pair. We're showing this in interval notation, lower boundary, comma, upper boundary. This is the area where f of x is greater than 0.